Now we can.
Yeah. Yeah.
Okay, so I say something. Yeah, it's really nice to be here, seeing all of you. You're so relaxed. Can you hear me now?
Neely's checking now if it's. It should be all working well, or fairly well.
But it's quite important during the Q&A, isn't it? When online people can.
You'll definitely on Zoom audio now.
I definitely what?
On Zoom audio. So in
Yeah.
other words, like, you can be locked with your speakers.
Yeah. Okay.
Yeah, this is great. This is great.
Okay.
Online thing. Yeah. So you need to check it, the presentation thing, the screen. Can you see that? Yeah.
Let me have a look at what's it like in there. You can see that. You can read it off here. Yeah.
This one, Tom's presentation. I should read this on the green.
I think you don't take your thing away because I don't know whether I can read this. Oh, I can read this from that far. Oh yeah, I can read this. Yeah. Well, it may not be. Don't you think? Yeah. Yeah. So that laptop is driving this, okay?
No. That's just testing for the online attendees.
Oh, right, okay.
This one, I already did that. It was not working. Try it again. Try it again. So this is live. And oh. What's good for the attendees? This is duplicating. This is so what we can do?
I can rather sit a bit further up with my head. It just have to lift up there. Have you listened to Bob's talk before on the? Yeah. What do you think? Do you get to make anything out of it?
We tried this.
Very difficult to make projections, especially about the future.
That's right. Well, this backcasting, I think John Christie's work is really important. You heard about John Christie? No. Yeah, a climatologist in Alabama.
So, right now the screen is coming with notes, which should
measuring climate data for over 35 years.
Before, they also have.
So can you just laptop for slides and have what's here? Is it like?
This Machete's, you're probably familiar with Machete's
I think last time
graph, transition graph.
Yeah.
Okay, I'll stop.
That's your water. Can you pass my water here? There. Thank you. Thank you, thank you.
It's okay.
Disturbance.
Just trying to distance some
This process always takes
Yeah.
If you want to separate silicon from the wall, this is the same question you asked in the seminar. Showing the wall together, and both of them are fragmented ambient.
I brought my 10% bag. British Princess.
Oh, I
I dated it
remember.
to about 2009.
I love it.
That was going to be 10% of UK electricity consumption by 2010,
Yes.
and it didn't make it.
Didn't quite make it.
No.
Didn't make it by a lot. It didn't make it by a lot.
Yeah.
The lift off was a bit greater.
Yeah.
So, do you know why they didn't make it? Is there any reason?
Wind turbines were too small and weedy to start with. So
You need bigger one. Yeah, it was more. I know.
and Derek was still trying to hand carve them.
Derek Taylor.
Yeah.
So I need to try everything.
No lack of enthusiasm. No?
Yeah,
So
well, there should be this one, but it's not turning on.
no, it can turn on. I can do that. Can you just come up? This is see here.
Closer.
I think we can do
Yeah.
this. Extend.
Oh yeah.
One of the consequences of that was
We can do this. You can turn it on. Yeah.
Oh, so you fixed it?
Let's see.
Yeah, there we go. Yeah, perfect.
Now do it.
Click keep changes. You have to do the same thing again.
Don't push the button. It's already on.
And then click keep changes. Okay, now you can, now it works, now it works.
Now what do I do? Now do this. What was this? This one?
Just click screen share.
Oh. Now all windows?
Yeah, like that. And then now, when you move this one over to this screen,
Yeah.
and then when you click slideshow it will work.
Put it somewhere else, not here.
Because you have to flip them.
Keep your cup. Yeah, keep a cup. Just put it over there.
So turn on the microphone because right now. For the right now you can connect the microphones like this.
Yeah. I can't, the button is on icons.
Okay.
I think everything is prepped now.
Turn it off.
I think, and we have Schumann.
Oh yeah, because of Bob is talking.
So you want me to wear
There's,
a device or?
unfortunately, there's only one. So I'll have to wear it first, and I pass it to you then. To my phone last. Yeah. Ah. Thank you. There you go. No, I just switched the screens to this one.
Okay. Microphone working, camera working. Okay. Online is fine, here is fine. Last meeting is fine.
Short presentation to start with.
Yes, just introducing what is the seminar, who's speaking today.
So I thought
Yes. Okay. Yes, please. And then I'll yeah. We've also we have a short break in the middle, which gives us some time to
fly around.
yeah, pass it around. Okay.
What do you find online?
Everything.
You can position the camera to the speaker, and we can start in pass on to Bob, then he will pass on to Michael. Hello?
There we go.
Starting in starting in 2 minutes. Let's start in 2 minutes.
Can you do me a favor?
If they're expecting that, that's not it.
No. Is that wrong?
Yes.
How so?
A reflection on my PhD.
Oh. Ah. I see what I've done. There we go. There we go. There we go.
I think it was the last presentation.
Oh. That was okay. There we go.
We can check
Thank
it
you.
out.
Thank you. I didn't end up doing this transition for all of them. Only some of them. Here we go. Have we? Would you like This isn't mine, so it's okay. This is the university. It's okay, you can still.
I'm fine. I've plenty
So before it starts, I did a thing on the first an isotropy that saw faster liquid transport through the horizontal axis, so slower thermal transport through the horizontal axis. So if you imagine if you're printing a panel, if you 3D print it flat, it will behave like this. If you print it flat and then rotate it, it will walk over here.
So you're going to do something like that?
Yeah.
I'm trying to get rid of one of my
I think this will be starting in a moment. Okay, is everybody in the room? Hello, everyone. We're about to start. That's okay. Is everybody in the room? Anybody missing? No. Okay, we're good to go. We're good to go. So welcome all to the fourth ERBE seminar focused on energy resilience in the built environment and sharing the skills we pick up along the way. The series is hosted on the last Wednesday of every month, inviting different speakers to come along But first I'll get into who's hosting this and why are we hosting it. There we go. So firstly, we have the CIBSE YEPG. I didn't. Can you check the, hello? Oh, okay, so welcome all to the Energy Resilience in the Built Environment seminar series. This is co-hosted partly by the CIBSE Young Energy Performance Group, who's a part of the Chartered Institute of Building Services Engineers, a subgroup of the Energy Performance Group, which happens to be the largest special interest group within CIBSE with over 23,000 members. Then inside of that, the CIBSE YEPG looks to share innovative ideas and research in building energy performance, providing a platform for discussion and dissemination, reaching out to young professionals, enabling network opportunities and promoting collaboration and supporting professional development. So how does that relate to ERBE? ERBE is a CDT based on cohort training for doctoral researchers, encouraging knowledge sharing, mutual support between academics, industry, and government. So we want to reach out and we want to share our information and get presenters from other people so we can work together. Then what is this seminar? Well, we want to provide a range of perspectives on a given issue to hopefully provide more nuanced and rounded perspectives on these issues, as well as growing passion for building energy, building a stronger network, and sharing ideas to encourage discussion. Then, what is energy resilience? Well, before we get into the presentation, energy systems are held in a trilemma between emissions, security, and cost. The ideal system would provide all three, but this is difficult. So it's our job to consider ways to deliver affordable energy to consumers to protect fuel-poor households and energy-intensive businesses, while tolerating disturbances and system shocks, while also maintaining low emissions to meet climate targets. This is tricky, but how do buildings relate to that? Well, we can look at providing a flexible system. With the introduction of intermittent renewables, we don't have the same rapid response gas generators or piles of coal providing months of stored energy. Therefore, we should provide flexible buildings which can consume energy from the grid, aligning with renewable electricity generation. To do this, we might consider the factors influencing building energy consumption. These options might include increased insulation to reduce heat demand in winter when renewables are generating less, or perhaps we might look at how occupants can turn down their heating set points to reduce demand, or we might provide more energy efficient services to reduce demand. There's all kinds of different solutions to better utilize the low carbon intensity renewables that we have available. Now we'll get into the presentations. Today we have two fantastic seminars on the dynamics of the energy system transition at the global level and its implications for the UK built environment. So today we have Dr. Laifeng Xu, who is a principal research fellow at the UCL Energy Institute with the ambition to contribute to the establishment of socio-technical perspectives on energy demand through research, teaching, and PhD supervision. Then we have Robert Lowe, who is a professor and the chair of Energy and Building Science at UCL. In 2009, Bob and Taj established the UCL Energy Institute, which he directed between 2014 and 2018. Bob is a physicist with a broad interest in the field of buildings, energy, and sustainability. Now, the agenda for today. First, we have this short introduction, then we'll jump into Bob's presentation for 50 minutes. And we have a 10-minute break in between before another 50-minute presentation, followed by a Q&A and networking. I hope this is all okay, and let's welcome Bob to the stage. Is this the right one?
No, the other one. That's it. Hold on. Thank you.
laser pointer as well if you wanted.
Brilliant. Yes, thank you.
I didn't connect it for the slides.
This is a remarkably strong spring. Maybe if I just swallowed it, it would work better. I'm not quite sure what to do with this, actually. That's yeah, maybe somebody else can actually see what they're doing. Can you clip it to my, yeah.
Yes. There we go.
I was probably doing something wrong. Right, yes, I can hear that we've got room audio, that's fantastic. So the first thing to say is, yes, I did grow a beard between when the photograph was taken and now. I'm not standing in for Professor Lowe, I'm Professor Lowe. This is the topic of my lecture. And before I begin properly, I just wanted to say a few words about Jevons. The first time I presented this talk was actually in the Jevons room at UCL. And I just wanted to remind you all, if you haven't already done so, to read Jevons' book, The Coal Question. It was only written about 140 years ago, so it's still quite up to date. And it's one of the most interesting books on energy that you can read. So there we go. Let me see if this works. Yep, okay. So what I want to do today is to talk about some of the factors that drive energy system transitions. This talk springs from a paper that I wrote with Paul Drummond, a colleague at UCL. And the paper was, the title of the paper was Logistic Substitution in Global Energy Demand. So if you, you'll find the reference at the end of this lecture, and presumably the lecture notes will be circulated to anybody who wants them. And part of what I'm doing is to reflect on the process of writing a paper like this. So where do the ideas come from? How do you get your ideas to write a paper that can get into a journal? And about some of the interesting twists and turns through the process of writing the paper. Okay, so factors that drive energy system transitions, going back again to Jevons and to people like Malthus, Thomas Malthus, people like King Hubbert and Jean Laharrière, who is still with us at, I think, the ripe old age of 101, and recently published his latest journal article. So this is something. You have decades of aspiration and endeavour in front of you, if this is anything to go by. Poverty and potential as a and this is technical potential, as a stimulus to innovation is the second category of drivers. And the third is the availability of an as yet unexploited resource, and the emergence of a new technology or cluster of technologies, perhaps harnessing new physical principles to exploit it. On the subject of new physical principles, some of you may remember the lecture that I gave at the beginning of our block week that you will have attended about 2 years ago, something like that, 1 September. And I talked about steam engines because whenever I have the opportunity, I talk about steam engines. And one of the things to think about here is that as far as I know, there is no biological equivalent of a heat engine. Biological life on this planet, as far as I know, does not use the heat engine at all. Instead, it uses systems that are much closer to fuel cells than heat engines. So the invention of the steam engine was a very good example of a new technology harnessing an at that time unexploited resource using a new physical principle. Okay, so moving on. Yeah, and by the way, when you've finished reading Jevons, I also suggest that you, if you have the stomach for it, you read Thomas Malthus. Very, very interesting perspective on the situation in particular, the demographic situation in the late 1700s in Europe. Okay, so some more factors driving energy system transitions. Learning, which is typically defined by economists as the fractional reduction in cost per doubling of installed capacity of some category or other of technology. Now, the Industrial Revolution, at some point I'll come into the 20th century, and then I'll move into the 21st century, but not yet. The Industrial Revolution was driven by a 40-fold reduction in steam engine efficiency between the mid-1700s and the mid-1800s, which simultaneously reduced both the specific size and mass of steam engines. Now, we are often used to the idea that if you make something more efficient, it tends to get bigger. Heat exchangers get bigger. Cooling systems on power stations get bigger, and so on and so on. And all of this is true. It is really interesting then to look at the effect of efficiency gains early in the Industrial Revolution, which shrank machines dramatically. And all of this was possible because of the enormous inefficiencies of the earlier steam engines. But learning eventually saturates. And what we've got here is a little graph. I spent the weekend doing this. Let me see if I can work out what's going on here. The vertical axis is the remaining thermodynamically limited efficiency improvement. So that is how many times better you can make a particular class of technology before you hit the limits as defined by, for example, the laws of thermodynamics. And in the case of steam engines, which are the blue dots, you can see what's happening. We're heading down from, as I said, a ratio of approaching a couple of orders of magnitude in the early 1700s. At that point, steam engines were about 50% efficient. Sorry, 0.5% efficient. 0.5% efficient. And simply by raising the operating temperature, or the steam temperature, from 100 degrees centigrade to 110 degrees centigrade, you could something like double the efficiency of the steam engines at that time, because the steam cycle that they were working with was so crude and inefficient. It took Carnot to explain why doing that worked. But as is almost always the case, the engineers were ahead of the physicists. Engineers invent stuff, and then physicists explain how. I've also got lighting there as well in red. And there are wonderful papers on lighting, including one by William Nordhaus, economist who's been working in this area for many, many years, who doesn't quite understand, I think, what he wrote. But I've taken some of the data for this graph from his paper, some, I think, from other sources. And what you can see is that we are approaching the quantum limit of lighting efficiency. If we want to make lighting significantly more efficient, at some point we will have to bioengineer eyeballs and retinas and the cone and rod arrangements therein, because in the frequency range that we operate in, we are very close to the limit now. Okay, so the paper, back to the paper. How did the paper get written? This is an early doodle for the paper. And what I did here was on the back of electronic envelope, Excel. I always reach for Excel at times like this. I plotted the energy output, global energy output of wind, PV, and total primary energy on curves. And you can see wind here in red, we have a pointer. You can see, okay, let's try this. Yeah, okay, you can see PV is green, total primary energy is blue, and the residual primary energy, which is total primary energy minus the renewables, I predicted would do this. Now, one of the things that you can do is you can reflect on the likely consequences on the rest of the global economic system a few months after this happens. Okay. Basically, you've just built the biggest production chain ever to make all of this stuff as fast as possible. It's growing exponentially. So the rate, the capacity for producing PV, for example, is increasing exponentially all the way to here, and then it stops. Okay, nice to be able to turn this off at that moment. So there's a big bang. You can picture this as a flight path, a possible flight path to Heathrow. You wouldn't want to be on that aeroplane. Where are we? Okay. So, okay. So the conclusion from this is that the tentative conclusion from this is that constraints on growth at the end of a transition must mirror those at the start. At the start, we have a new technology, an insurgent technology, which slowly rises from next to nothing, starts to increase exponentially for complex reasons. The exponential function seems to emerge in all sorts of places in economic and industrial systems and human ecology, and indeed ecology generally, but in complex ways. It's not trivial. So constraints on growth at the end of a transition must mirror those at the beginning. You need a smooth asymptote. And in that case, real-world transitions must be S-shaped in some way. Okay? That is a piece of abstract reasoning. It is difficult for me to, it's impossible, I think, for me to prove that statement by collecting data and analysing it. I don't think that works. I think that is a piece of abstract reasoning which you either buy into or you critique. And if you want to critique it, we can critique it after this meeting and argue the toss backwards and forwards about whether real-world transitions must necessarily be S-shaped. Okay, where am I going? Whoops, I'm pressing the wrong button. Okay. Okay, so then I reflected on this and I realized that I had seen this graph in A New Scientist in the 80s. Okay, I thought, maybe I can use that because the report that this is based on, Dynamics of Energy Systems and the Logistic Substitution Model, by Marchetti and Nakicenovic, was all about S-shaped substitutions, or partial substitutions. I will explain why partial later. I will talk about partiality of these. Okay, so here we are. The first thing to note about this graph is nonlinear axes and a rather peculiar measure of penetration of the new technology into the energy system as a whole. Marchetti and Nakicenovic did this. Let me just call them M and N, please, then I won't get mixed up. M and N did this so that they could, first of all, fit transitions substitution processes onto finite graph paper. So that was quite important. They needed to be able to boil all of this down into a single small piece of graph paper. And secondly, because the S-shaped functions that they were using appear as straight lines on these graphs until something else acts to prevent the growth of that technology and something else takes over. So what can we see? We can see a succession of technologies. Here we have wood declining. Okay. Interestingly, though, I'll come back to this in a few minutes, the world is using as much wood now, burning as much wood now, as it's ever done.
You stole my line.
I will have forgotten that by the time you reuse it. Please do likewise. Yes, indeed. Okay, then we have coal. Then we have oil, which really started taking off in the 1870s, thereabouts. Sorry, petroleum. There was always oil, but this is petroleum. And then natural gas, then nuclear, which got as far as this. That's about an inch on my graph, because that was the date of the report. Yeah? Okay. And the rest is projection, up the graph paper projection. This thing called sulfus, Marchetti and Akachenovich thought there would be something after nuclear, by which they meant fission, and they didn't know what it was going to be. So they said, well, maybe it will be solar, maybe it will be fusion. That means distant fusion and local fusion is another way of thinking of that. And so they called it sulfus. Moving on. Okay, this is what they wrote about substitution, which is generally unexceptional, except that you can disagree with bits of it. Substitution of a new way for the old way of satisfying a given need has been the subject of a large number of studies. One general finding is that almost all binary substitution processes follow characteristic S-shaped curves. Okay. Moving on. And the question that Paul Drummond and I had to face was, well, which S-shaped curve shall we use? And there's probably a chapter in most degree level maths books about logistic curves, because there's a number of different ways of making an S-shaped curve with algebra. I wanted something that had a small number of parameters, and because of my limited and declining mathematical ability, it needed to be simple. So it had to be something that I could understand, otherwise I can't use it. So this was the functional form that we chose, and things in quotes will be quotes from the paper. So let's just run through this very briefly. So what this means is that the penetration of the new technology into the energy system as a whole at time step t+1 equals the penetration at time step t times 1 plus alpha divided by 1 minus f at t, where alpha is a thing that I referred to as the intrinsic growth coefficient, or which is equal to the incremental growth coefficient of the insurgent technology when f is very small, at very small penetrations. At that point, you can see that that gives you, in discrete form, an exponential function. Yeah? If it's not obvious that that gives you an exponential function, find somebody at t who thinks they understand why that's an exponential function and ask them to explain it. It is very simple. Yeah. And then the extra tweak was finding a way to cope with more than one technology. So I wanted us to be able to include at least 2 separate technologies, insurgent technologies, in this analysis. And so we expanded this bit of the equation basically by summing over the penetrations of all of the insurgent technologies. And that actually worked quite nicely. So, as it says here, this form is appropriate when the insurgent technologies are not competing with each other, but each competes with the previous energy, the incumbent energy system. These are all assumptions. Again, there is nowhere where you can put your thermometer or your temperature sensor and actually demonstrate that this is happening. These are all assumptions. This is a conceptually led paper. Okay, I've done that. You can come back to that if you want to, but yeah, okay. This is the share of the insurgent technology, and this, therefore, is the share of energy provided by the old fossil-dominated system, the incumbent technology. Good. Okay, then the next thing that we wanted to take into account was the fact that if you electrify things, they tend to become more efficient. So we built a simple, we did a simple sectoral analysis of global energy use with, I think, about 5 categories. And I was able to persuade myself and Paul Drummond that the ratio of conventional primary fossil fuel energy displaced by a joule of electrical energy was about 0.7. In other words, there is a small energy efficiency gain from electrification at the global level across all categories of demand. And 0.7 is sufficiently close to 1 when you have rapidly growing, when you have high intrinsic growth rates, that it doesn't really matter. So we called that 1 to 1, just to make life easier. Okay, we tested a number of limits, possible physical and other limits, economic limits to the rate of growth of the insurgent technologies. We looked at the land and sea area occupied by wind and solar, which is an instructive thing to do, actually. I mean, it's almost worth doing it yourself. It doesn't take very long. And you realize very quickly that it actually matters where you put stuff. So in the same way, for example, that petroleum engineers tend to prospect for oil where they think there are oil-bearing rocks, it makes sense to put wind turbines where it is windy, and it makes sense generally to put solar panels where it's sunny. And that isn't always obvious. One of the funniest reports that you can read, I think it's still available online, is the Warwick Wind Power report, which is now about 20 years old, which was looking at the efficiency of urban wind and showed that some systems actually produced positive electrical output, but many systems used more electricity for their electronics than they actually produced, and so had were net negative producers of electricity. Don't put wind turbines in towns. It's daft. Okay. What else? Yeah, we looked at fraction of energy in global wind systems, fraction of incoming solar captured by PV, fraction of energy, wind energy captured by turbines, and so on and so on. You can read all of this. I think one of the more interesting ones that we looked at, but not as thoroughly as perhaps we should, was the ratio of cumulative metal requirements to reserves and resources. And I shall loop back to that later. Okay. Okay, here is a stylized S-curve using the function that we, functional form that we chose. And I've graphed this for an intrinsic growth rate of 20% per year, which is in roughly the right ballpark historically for wind and PV. Wind and PV growth rates have gone up and down over time. We graphed that because we wanted to understand or try to understand what the variability of growth rates had been. One of the things to reflect upon is the relevance of the transition from PV integrated into the earlier Sinclair pocket calculators, the 4-function calculators, and PV integrated into later, more powerful calculators, and whether the same processes would have been at work when that was happening in the 1980s. I was there in the 1980s, and as are happening now, as we're starting to integrate PV into grids at the gigawatt scale. My suspicion, I doubt whether the processes are the same. They may be analogous in some way, but they are not the same processes. So the idea that we can put all these data points on one graph and draw an exponential through them is bold. That's the word I'm looking for. Bold. That's a bold move. Okay, and I keep on reaching for the wrong button. Okay, there is the fossil output, and the horizontal line is years from the 1% share mark. Now, the awkward thing about these logistic functions is that they break down at the very low end because they predict an infinitely long tail going back into history of photovoltaics and wind and whatever the insurgent technology happens to be, and that is obviously not the case. Things must start somewhere. Declining effective annual growth rate. So the effective annual growth rate is the intrinsic growth rate modified by the declining share of consumption, which is still available to be captured by the incumbent. F divided by 1 minus F. I did that because I was desperate for it to be a straight line, and it was a straight line, so I was happy. That meant that I hadn't messed up the maths in my spreadsheet. I am sufficiently mathematically challenged that I have to do these obvious checks to make sure I haven't garbled stuff. Okay. Annual increment of market share starts low, goes up exponentially, peaks, and then goes down. Is that obvious? That's probably obvious to some of you. Some of you might have to think about it. Okay, but it's a consequence of the idea that technology substitution is S-shaped. Now, I had a go recently, in the last few months, at estimating crudely the fossil fraction of investment. And I'm not quite sure what happens here. Yeah, there we go. The fraction of total investment which is being generated by the incumbent economy. If you think of the world economy now as actually coming in two parts, a renewable economy and a fossil economy. The fossil economy at the moment is doing providing most of the investment for the growth of renewables. That's just the way it is. I mean, the economy is big, it's complex, it's highly interconnected, and the idea that you can actually separate out the bit of the economy which is renewably powered is, again, bold. I like that word. I'm going to keep using that word because it's better than ruder words that I could use for that error. Okay, so support for the old from the new. I hope this works. Yes, I love it when that happens. Okay, what we're looking at here is the flow of investment from, and this, you have to interpret this conceptually. I don't know how you would measure this in practice, because as I say, the two economies are one, and I don't know how you distinguish between what is coming from fossil and what is coming from renewables that you've already installed. But I think that's justifiable. We can argue about it over tea. And this was, if you like, the punchline. I think this was figure 1 or something in the paper. And it looked like we got carried away with functions on this graph because there are too many. So let me see if I can explain what they are. Let me see if I can remember what they are. Okay, so the blue line here is total primary energy consumption for the whole global economy. The dashed line here is how that would increase if you decided to install significant amounts of carbon capture. And the technology that we had in mind here was DACS, direct air capture and storage. Okay. The reason for wanting to do that is that we wanted to say something about what hitting a net zero by 2050 target would mean in practice. And obviously with a logistic function, you can't hit a net zero by any when. Not by 2050, not by anyone else. So this was our rabbit out. This is a poorly integrated rabbit out of the hat, poorly integrated into the logic of the rest of the paper. We ran out of steam, but happily the reviewers ran out of steam sooner. So we were okay, and we got published. That's the trick in getting stuff published. You need to make sure the reviewer runs out of steam before you run out of steam. Then you get published. Okay, and we had 3 intrinsic. I shouldn't. No. Most of the pleasure that I got from writing this stuff was actually in the writing and in the spreadsheets and in the back and forth with Paul. And getting it published was the icing on the cake, but that's quite thin. There are 3 sets. There are 3 pairs of curves on here for different growth rates: low, central, and high intrinsic growth rates. And I think you can see that at the lower growth rate, you're not getting close to net zero until well into the second half of the century. So, I mean, I hope to be able to see this. I shall be 95 then, and I'm looking forward to seeing that. But I very much doubt if I'll see anything out here. So, but you might, that would be good. Okay. Okay, so more thoughts, and this is taken from the paper. The topology of the energy system and the nature of individual subsystems would likely alter substantially with high levels of solar wind. In other words, because coal mines and oil fields are not generally in the same place as it is sunny, some of them are, but not always, and they're also not generally in the same place that demand is located, although in some cases they are, you would expect the architecture, the topology of the whole global energy system to reorganize itself through this transition. And indeed, if you look at the transition into fossil fuels, that caused a massive reorganization of patterns of trade, of military power, and so on and so on, which I will say a few words about at the end of the lecture. Referee, how long before half time? I will get going. I'll get going. I can probably do this. Okay. Okay. So and this introduces, by the way, the idea of energy system architecture. I'm not going to say much about this because I'm running out of time, but all complex systems have form, have structure, have organization, have an architecture. I have an architecture. It's an architecture which was laid down essentially by the very first bony fish, which arranged to have 2 pairs of gills, the ones at the front and the ones at the back, okay, and a tail, which I've since lost. I've lost the tail, as have you, but it's kind of there in a vestigial form. We have an architecture, and the energy system, the global energy system, has an architecture. Okay. So, going back to Marchetti and Nakicenovich's, you have to practice that. You have to practice Marchetti and Nakicenovich in front of the shaving mirror in the morning. Those of you who shave. Those of you who don't shave can borrow a shaving mirror and practice it. So this is what we called Solwyn, in a nod to Marchetti and Nakicenovich's Solfus. We thought we did know what it was going to be. Maybe we do, maybe we don't. What you can see is that it is certainly based on historical growth rates. It would be the fastest energy system transition ever to have taken place. And if you believe that there is graph paper out here to the left, it will be the first one that would go to something like completion. The others, none of them got past about 75%. Coal reached about 75% of global energy, but was then turned around by growing oil consumption and growing natural gas consumption. Okay, that's interesting. Where do we go next? Okay, I'm not sure where we go. Right, okay, so, yeah, but Solwyn has only just appeared on this graph. That's all the data we've got at the moment. And so it's fairly bold to just run that up the graph paper, even up the nonlinear graph paper. There is an earlier technology which showed early promise and then stalled, and that is fission, referred to here as nuclear fission. Yeah. So at these very low levels, technologies can come and go. And indeed, there is something about this graph which is about picking winners. So what we've done, what Marchetti and Nakicenovich did, and what Paul and I continue to do, was to focus on the technologies that we thought would win in the end. But maybe there are other technologies that we could find that could have gone on this graph that didn't in the end go anywhere. This graph, most of this graph is very backward looking. It's about history. And history always gives the impression of more inevitability than perhaps there really was. Okay, more comments from us. It therefore appears that the process of substitution is underway, which if continued, has the potential to displace fossil fuel from almost all markets between about 2050 and about 2070. Growth of Solwyn could in principle be curtailed by an as yet unidentified insurgent technology, but such a technology would have to be growing even faster than solar and wind have been growing up until now. And I can't see it. I can't see it. Such a transformation of energy supply will both require and drive a deep reconfiguration of global energy demand towards electricity and derived products. It's self-dependent on multiple other technological substitution processes across subsectors and geographies. Reflection on historical transitions, first from biomass to coal and then to oil, suggests that such a process would profoundly impact patterns of global trade and ultimately geopolitics, domains in which human agency is key, but which lie outside the bounds of our analysis, and are probably ought to be denied to a physicist of modest abilities who has been dabbling in energy for a long time but has never studied politics, geopolitics, or history formally. That's me, by the way. Yeah, okay. Press the right button. There are some lovely reflections in the Marchetti and Nakachevich report on the inevitability of energy system transitions. Here's a very good example. The smooth curves are two-parameter logistics assembled in a system of equations as described in the text. The fitting appears perfect for historical data. Anybody can make data look like a straight line by plotting it on logarithmic graph paper. Yeah? Almost everything looks straight, or at least sensible, on logarithmic graph paper. So, not so sure. The curves are now plotted, blah, 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 greatly helping visual inspection and formal considerations. The first fact to be observed is the extreme regularity and slowness of the substitution. It takes about 100 years to go from 1% to 50% of the market. We want all of this to be over in 50 years. We call this length of time the time constant of the system. Yes, historical transitions seem to have gone at roughly the same rates. We hope, don't we, that the transition to renewables will go 4 times as quickly. This regularity refers not only to the fact that the rate of penetration remains constant over such very long periods, but also the fact that all perturbations are reabsorbed elastically without influencing the trend. It is as if the system had a schedule, a will, and a clock. They've gone full on historical determinist here. It's really interesting, I think, what they've done with this. I suspect this stuff was written slightly tongue-in-cheek, but I don't know. I did have a conversation with both Marchetti and Nakachevich very briefly, but we didn't get into this level. This transition may be different. First of all, it's global rather than region by region. So in the transition into fossil fuels, the first thing that happened was that Britain and then the US and parts of Northern Europe got into fossil fuels, and then other parts of the world followed, and so on and so on. Likely taking place in parallel with the emergence of other energy resource constraints and in the presence of the largest ever global human population. Okay, so it's not just energy which is in short supply or problematic, it is also things like minerals and so on. And moving on, the Hubbert curve. How many of you have read any of M. King Hubbert's papers? Okay, this goes on the list for all of our students. I won't suggest reading by my academic colleagues, but students, do please pick up at least one of M. King Hubbert's papers and read it. This is a 1971 paper, and he predicted that fossil oil, petroleum, would peak around 2000 to 2010 or thereabouts. I think, I can't read the, yeah, something like that. And he's been proven wrong, but I think he just got the timing wrong. Okay, so there we go. So this is Laharère, Hall and Bentley 2022. I said Laharère was still publishing until very recently. He was, I think, 99 when he published this. How much oil remains for the world to produce, different methods. We don't know. To find out how much oil remains to be produced, we'd have to dig up the planet and analyze it, in principle. And everything else is an approximation, because we can't dig up the planet and analyze it. But this is what they thought. An additional feature of this is that the less oil is available, the harder you have to suck it out. The harder it is to suck the remaining oil out. And so the energy return on energy investment declines, and the energy cost of oil and gas extraction, which is this mustard-colored slice at the top here, grows. Here it was very small, you could hardly see it. In the early days, the heroic days of oil exploration in the 1860s, oil just came out of the ground on its own. not quite sure where I was going with this. So we'll, oh, there we go. Yes, okay, yes. Geopolitical implications of all of this. First, just look at the top here. We've got OW. Wait for it. What on earth was that? OW? Opium War. Opium War 1, that was it. Yes, yes. Opium War 1, Opium War 2. They're coming now. Now I've got the Opium War. World War 1. In between, there was a couple of Crimean wars, which may in part have had something to do with the discovery of oil in the Crimea, or in that part of the world. World War II. One of the interesting things about World War I and II was that, certainly World War I, none of the participants wanted a war, with the possible exception of Serbia. But the major countries involved, it appears now, didn't want a war. And one of the saddest historical episodes was when the Kaiser, Wilhelm, decided to write to, I think, the Emperor of Austria, the Austro-Hungarian Empire, to say, please don't go to war with the Russians over Serbia. And because he was old school and wanted to do things the proper way, he sent a courier with a letter which arrived after World War I had started. It's worth thinking about, the unmanageability of conflict, particularly as it approaches and once it's begun. Gulf War I, Gulf War II, Ukraine. Okay, I would submit, Your Honour, that these are all aspects of competition between great powers for resources and are driven, first of all, by the upswing of fossil fuels in the 19th century and then by the decline of fossil fuels, and in particular oil, more recently. How much time do I have left? 3 minutes, okay. A bonus of writing this paper was that I took one of my spreadsheets where I was looking at the amount of replacement capital which had to be funded through the transition. So the early wind turbines have to be replaced by more modern wind turbines because they wear out and stop working. And when I stretched the first version of this graph past here, I discovered this interesting oscillation. And I thought to myself, that looks like Kondratiev waves, which I didn't know anything about, but I'd heard about. I'd seen a picture of Kondratiev waves. Kondratiev was a Russian economist in the early part of the 20th century who was very interested in oscillations in regional and national economies. Okay, there we go. That's from his 1926 paper, which he published in German, Die Längenwellen der Konjunktur. And you can see that real-world oscillations are much messier than the very nice, simple oscillations on my graph. There we go, we'll ignore that. Things that interact here at the tail end of this transition are things like the physical lifespan of PV and wind systems. I took 15 years just to be able to show a graph, and the growth rate, the intrinsic growth rate. So that kind of illustrates that if you're lucky and you do some work like this, you'll discover stuff that you didn't expect. And I don't know whether I've discovered stuff that I didn't expect. I think there's something going on there. And if I find some time, maybe I'll dig into that more. Done. Stopped. References. The first one of which is Isaac Asimov's The End. Okay. please read Isaac Asimov's The End, which you can find going round and round on hard disks in a couple of places on the planet. It's a great short explanation of the foolishness of assuming exponential growth goes on forever. You'll enjoy it. What do I do now?
Okay.
Where do I stand?
So we have a 10-minute break now, and we're going to group the two Q&A sessions together at the end after a lifelong presentation.
Thank you.
And we'll come back and resume for the next presentation in 10 minutes.
If anybody thought that I'm going to be more than I was wrong.
Okay. Thank you very much.
Thank you. That was really interesting. Oh. Put this over here now.
I think Jean Horaire is only 93.
So you can't stop it. You just keep adjusting it.
I was saying I was just bored this house thinking for something. It is, part of it is that a lot of things you want to think about are in science fiction. And these come from the inner poetic world of science. And so I've been reading, where do ideas come from? Where do ideas come from? They are meta. Yeah. So this is why I worry about the global warming eco-act sinking into the collective unconscious and then popping up in Greta or what her name and stuff like that. Well done. Thank you. Go further back than Asimov.
So just stop.
This is a 10-minute break about people to take in all that information you've thrown out there.
What is good fun? The questions and sandwich for the teams.
It's interesting that you say it, because I want this observation that replacing all of our fossil fuel, and then we're building up this massive infrastructure to build all of it, and then we won't need it for 10 years, and so we have to replace it all. Something will have to change.
History of the and how they were built.
Yeah, it's just here. I'll set up your presentation now.
What we need
And then when you're ready to speak, you can flip it to unmute. It's on mute right now. And I can, if you want, it's a little bit tricky to put on your collar. I think you did. I think you did it already.
It's bad. With glasses.
Where you will be standing the most, you can place the camera.
Which camera?
This camera is for you.
You see, if I stand, you can't see me completely, you see. I can hide. No, it's okay.
People online are seeing you with this camera.
I see. You can't see me now. Is it me? Okay. So you want to do this? Maybe put it in a much lower side. Yeah. I don't know. You can't see me anyway because I'm so short. Have you got something that I can stand up?
I think it's okay. You can just pull it. Yeah. You can pull it down. Don't worry.
Can you lower this? Yeah. Yeah, that's better. Would they be able to see the sides then? Yeah. Oh, that's good. Let's see.
Have you heard that they made a
No.
series based on
Here. I need to have glasses.
Oh, you watch. I have the same thing. Yeah. Yeah, I didn't feel interested in how I could watch this series. I have a question, but maybe it's better to keep it for the end of the session to explain to what.
Can you hear me? Am I on? Can you hear me? Testing.
I think so. I think I can hear you.
Is it on?
Yeah.
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 So,
Okay.
am I right? Yeah?
Yes.
All right. Let's put it here.
Okay, everybody. The next presentation is about to start.
Can I have my laser pointer here? So my laser pointer can actually drive the
I can
flag.
put
So,
it in. I didn't put it now yet.
can drive the slides.
Let's see if this works.
Yeah. So I don't need this one. Yeah.
I'll try going out.
Yeah.
I don't think it's picking it up.
Does it work?
Which was an issue I had in the past.
So, wait, I can, if you want, I can just use it as, and how do you do this? Use a mouse. Or maybe you can help me
On
with
the
it.
arrow keys, you can just press
The
left
arrow
and right.
keys up and down.
If you
Up and
see,
down. Yeah,
yeah.
okay.
Any, yeah.
This,
Sorry,
left, left? Oh, that's it, okay.
Yeah.
Back, yeah, okay, okay, okay. Yeah, really, you're comfortable? Do I need to worry about this one? No? Yeah, no, I don't need to worry. Yeah, yes, because I can't see anybody. Sorry, it's so vertically challenged, you know. But nice thing come from small packages, right? So anyway, thank you for inviting me here. And my name is Laifeng, if some of you don't know me. And I'm just following, so I go back a little bit to the title. So this is the real title, really, of my talk. It's a dynamic of global energy system transition and its implication for the UK built environment. Yep, and you have heard what Bob's theory of scarcity and substitution in relation to global energy transition. Now, this part of my talk is about trying to concretizing such an abstract argument around scarcity and substitution in the context of the built environment. I will outline briefly the relationship between, first, mineral and material and energy resources that undergirding the built environment. Second, the economic activities stem from these transitions. And third, financial capital, and fourth, derivative and financial capital. The third and the fourth, unfortunately, with the limited time that I have, I can't really do very much about giving you any more detail than just a sketch of how it affects particularly the UK building industry. So you have to bear with me. So, but I will sort of go at the interplay of these several layers of the conceptual framework. Back to the future. The presentation of Bob's MNN in 1979 slide, the first impression you will get is what? Is a stage theory. One that is the energy resources replacing the other. Like wood would be replaced by coal, as normally people would thought that is, and eventually will meet and then coal will be replaced by oil and gas. And then we'll meet the target for clean energy, solar and wind on the right-hand side. Okay. How useful is a stage model for conceptualizing transition? Work up till now. So I think it's useful maybe for telling story, a wonderful story about Opium War 1 and 2, when the British and the airlines drove down to the Pearl River, that China hasn't actually got any coal driven or steam engine warship. Yeah, so that's why I'm here, because Hong Kong was ceded to the British. So there's some truth in that kind of stage, if you like. The coal was supposed to be the most important resources to stimulate the Industrial Revolution. And then Britain really ruled the wave at that time. Now, but we see in historian Jean-Baptiste Frostow's book, which I will recommend him to go out and buy tomorrow straight away, and to read at least the first few chapters. He gathered historical evidence to suggest that energy transition by stage is a misconception. Wood has been used, or more wood has been used from ancient time to now. That was the line that Bob stolen from me, and has been replaced, but it's not have been replaced. It has been continued to support the overall energy development, and it's much, much more. Yeah, and you'll see some data support this. Oil, we have seen the use of seed oil for lighting to the discovery of crude oil in mid-1800s. Seed oil has not disappeared. They are used continuously in various parts of the system for example, used for food and biofuels, you know. And we see people actually buying up, during COVID, buying up loads and loads of vegetable oil and put them in his Mercedes. Now, we want to phase out coal, but from 1850 onward, we have been using coal continuously, although the use of coal started to decline through changes in economic, social, political, for regulation and environmental pressures. It has continued being used in many parts of the world, still using a large number of it, notably in China, India, and in Eastern Europe, like Poland. Recently, maybe you have heard, has reopened its lignite plant, again after the Nord Stream blew up in 2022. Nuclear made its way in the 1950s. The use of uranium as a fuel has continued. There is a debate whether nuclear power should be part of the clean energy mix, and the advance of a small modular reactor may be a solution for more distributed energy system. So for me, I think, rather than energy transition is a replacement of one source by another, there seem to be a symbiotic process going on as human energy resources develop through the ages. Okay, that's Bob's. I'm going to steal your slide now. Bob's slide here presents a very abstract concept where fossil is in decline and renewable are inclined to replace it. The meeting of these incline and declines is around the inflection point. Bob said something around, is it 2030? Is that possible? Now, this graph, though simple, is very powerful. Yeah, because sometimes simplicity is a very powerful tool, but it's packed full of information with a lot of processes. Constraint and opportunity need to be unpacked, and I will going to unpack this gap in the next few slides. Yeah. Okay, let's introduce you to somebody really important in energy transition. You may or may not heard of him. Anybody heard of Václav Smil? One person only. Need to be more, right? If you're interested in the next several decades. Václav Smil is a professor of distinguished professor who has written more than 40 books on energy, material, and energy transition. His main argument is that there are 4 fundamental materials that make up the modern civilization. Here is steel, ammonia, cement, and plastics. And energy is required to produce this material. And I'm sure everybody knows how cement is produced. Without this material, modern civilization simply will collapse. Modern civilization. Yeah, I don't mean the nomadic civilization. Maybe there's some hope in that. So let's look at the built environment. How to curate a built environment. I know most of you actually work on buildings, but I think to be fair, if you really want to any transition in the built environment, you have to look at it this way. The built environment should include not only types of building, but also system of infrastructure that support them. In cities, large panels of precast concrete system are used to create office blocks, as you see over there, and high-rise flats, changing the skyline of our cities. Reinforced concrete is now inside every large modern building and every transportation infrastructure from port piers, tunnels, to roads and runways. So you see, you need that infrastructure system to support the buildings. So quite often, we seem to neglect that. That's really part of the system of your built environment. Maybe some of you don't, so I will apologize for that. Okay, this is a long, old photograph. Bob and I visited Rome. The example of the road of concrete in civilization, you only need to take a look at the Pantheon in Rome to see the concrete has been used since then. And what is concrete? Concrete, most of you probably know, is a mixture of sand, small stone, water, and cement. Cement is a key ingredient that makes concrete special. Heard of Portland cement is the most common form, 3 part limestone to 1 part clay, which has been heated to around 1500 degrees centigrade and then ground down to a powder. 1500 degrees centigrade, so that's really energy intensive. Indeed, my early days in England, I actually worked for civil engineering company, so I was dealing with ready-made concrete, the firm. So I'm not sort of that unfamiliar with concrete and not just only getting it from the book. I used to work up with a civil engineering company. The production of 1 cubic meter of concrete required 2,775 megajoule of energy. Coal, petcoke, and electricity are the dominant energy sources used in cement plants. Concrete is the most widely used manufactured material on the planet. It has shaped so much of our built environment, but it comes at a massive environmental cost. We use over 4 billion tons of concrete globally every year. Cement production alone generate around 2.5 billion tons of carbon dioxide, about 8% of the global total. Okay, that's my framework, yeah? To understand the energy transition, you have to look at it in a context, or these several contexts. We need to understand the relationship between the material and socio-technical and economic and financial layers. So I put the material and minerals right under there because I think it's foundational. Yeah, without that, we better go to Mars, perhaps. And the economic activity stem from it. But it's actually most important now in modern day, the 2 other layers, the financial capital 1, I call it M1, derivative financial capital M2, some people call it M3, are most important at the moment, driving energy transition. Yeah, they are. These financial systems drive energy transition. Believe me, you need to pay attention to that. So due to the limited time, I will only focus on the UK built environment and sketch out some of the content of this layer that implicate in energy transition. Let's start by looking at the physical and material base of what are needed in the transition in terms of building net zero homes or buildings, infrastructures. Building-wise, we can talk about retrofitting. Yeah, I think you probably got blocked out there, but I should read it to you. We can also talk about retrofit and new build. They more or less need the same material. As you know, retrofit, you need steel, concrete, glass, plasterboard, insulation, new building services, heat pumps, PV, new build need all the above, plus the infrastructure. If anybody see a big development like in London, they actually come with infrastructure, like for example, in Woolwich or Greenwich. When Woolwich want to build Barclays, is it Barclay? Barclay want to build this big development there. They asked the council for land. They had to promise, to support the building of the Elizabeth line. So the infrastructure is very, very important for the built environment. And also, if you look at over the side, if you actually have this infrastructure building, you need to strengthen the grid. Yeah, you've got more houses, you've got the infrastructure. The grid will require, when you start digging up the road, replacing the cable, you require roads construction, network of cables, pylons, and substations. Particularly in increasingly what we call that we want distributed energy system, a PV farm here, wind farm over there, then we probably need a lot of restructuring. That's what Bob was talking about, energy system architecture. So that's why we are interested in the development of system architecture in the future. And solar and wind generation. What about supply chains of PV panels, thermal solar, and the market economy? Okay, before that, I move on to that. Let's dig a little deeper. We need to understand how important fossil in our everyday life. Yeah. On the right, we can see crude oil is refined to produce product that we use every day, from butane, gasoline jet, if we want to go on a holiday, or you want to go home, some of you, diesel and fuel oil, to bitumen, asphalt, paraffin wax, plastics. Plastic specifically is oil product. It's embedded in most equipment you can find in hospitals and clinics. And you know your rails, your pharmacy, factory, all the, well, you can see it here. It's all from oil, right? On the right, you can see how ironic that Just Stop Oil activists use paint, which is a product of oil, to damage a valuable painting of Van Gogh hung in a museum. And these are symbols and representation of Western civilizations. Yeah? I might be apathetic about it, but if you love Van Gogh, yeah, it's history. And Van Gogh is a product of accumulation of the Western civilization. Yeah? And the museum, the building, the museum, again. And to throw paint in a painting, a paint come out of oil. Okay, that's how ironic that is. Pee-wee heat pumps are make a special sand. Let's see if, yeah, so let's, I got this. Let's take a little bit deeper. Yeah, looking at this slide and wider. As we build, we can see here, we need JCB. Can you see that? And which one should press? Yeah. Can you see that? Yeah, make of steel, rubberized wire for electric and hydraulic scoops. The concrete pour onto the foundation. Okay, and for walls as well as floors. Even the cranes are made of steel. So here, all the cranes there. Remember? Here? Yeah, there. Yeah. So heat pumps, so sorry, I haven't finished with that. Wood, yeah, going back, the wood. More and more wood are being used in building sites, yeah? And some of the usual things you see use of wood these days are pallets and transporting building material to and from sites, okay? And food, transport from pallets. So therefore, Bob is absolutely right. More and more wood are being used. It hasn't gone away, but it's just not used for fuel. But there are pallets used for fuel and so-called biofuel in somebody else's, maybe Marks and Spencer's boiler. I'm not telling you, may not be a secret now. The expansion of the grid would involve many wires and steel. And if we are to install AI to monitor and control the increasing intermittent supply of distributed electricity, more material will be used across the system. And the augmentation of electronic in future smart grid will involve, let me just flip the page, an increasing number of data centers. Yeah, you see that? Around the country. And more energy will be required for processing this data. Perhaps you already know that Microsoft is considering acquiring 3 Mile Island. Anybody heard of that? And Amazon is building a small nuclear reactor next to their data center. All the above indicate a whole host of economic activities, right? This layer, yeah? Trading, transport and travel, airport and seaport, etc. And services management, your people collecting your rent, and management administration center, as well as universities. Yeah? These are all can be found in London and some in other big cities. Okay, this slide tells how economic activity change over time. These changes implicate the acquisition of a variety of materials, mineral and products. We have been transitioning for quite some time now, not just the last couple of decades. From 1990s, I would say even from 70. Look, usually you find data always from 1990, but you can actually go right back to 1970s, which I had a slide when I was doing System Shock. And I would say in the 70s, UK has already been deindustrialized. When Sheffield no longer produced steels or silverware. Perhaps the recent closure of the Tartar steel has completed this process. Construction has changed much since, haven't changed, as you see, in construction machines haven't really changed very much, even now. But manufacturing decline, sorry, you can't see the points here. Can you see it diverge? Yeah? That is services. Unfortunately, it covers up the services here, and construction and manufacturing. Can you see this? Minus, manufacturing come down minus 8 points. Service increase to 10 points. Yeah? It's a big gap. Okay. This picture shows decisively UK economic activities are service-based. Yeah? No doubt about it. If not, go on. Okay. In order to see economic activity and the health or something to do with the health of the economy, you have to see the export and import. And there's always a lot of myths about, well, everything is come from China or whatever. Okay, I'm going to show you what the export and import to and from China is about. It's a bit difficult to see from here, but you can see on the top of the list, China export to United Kingdom around 16.87 billion is electronic equipment, something like this we're using. And, United Kingdom exporting pearls, precious stones, metal, and coins. And the interesting thing here also about China is exporting to United Kingdom machinery, nuclear reactors, and boilers. But they do the same. Now, what's going on here? For the third item here. Yeah? Well, what happened is quite often products as such, it's going to travel around the world. Yeah. So come here, go there. That maybe really like Bosch. Bosch actually have factory in China. Okay. So again, you can see furniture, lighting signs, and prefabricated buildings is exported to us. Yeah. And we export pharmaceutical products to China. Now, people might say that, why? Because we have a, reasonable pharmaceutical industry. Go on and go on. And here, plastic, they're coming back to us. But recently I discovered most of the waste plastic are actually sent to Hong Kong. And it was just being left in the wasteland and not processed. So there's a lot of things going on here. Well, if I leave you, but you can see this number. It's 81.2 billion. Yeah, coming in. We're exporting 33.4 out to China as a pattern. So what do we see here? What do we mean by actually looking at this situation? Yeah. So why do this matter? Because anybody can tell me why do this matter? This is very simple, actually. Somebody who read, why export, import, export, such a difference? There is a trade imbalance here. So why trade imbalance is important? So going back to Smith's fundamental material, I want to actually make it even more vivid to you. Is by looking at the trade side on timber, wood. UK is trading with actually many partners here, not just China, but with timber. We import timber from China, Germany, Sweden, and United States, as well as Finland. And there are also 181 partners here. So if you go to this site, you can play around with this. Yeah. And metals. Oh, no, not yet. Sorry. It's glass and stone. So UK partner from Canada, United States, Kazakhstan, Switzerland, and South Africa. Metal, okay, very important building material. It's important also from China, Germany, Italy, Turkey, and United States. In fact, United States is our biggest trading partner. Isn't that why we always want to follow what the United States said? Yeah, without United States, we are up the country. So this slide sums up the UK, the import-export of construction material, which you can find on the web. It's a government publication. And it shows the times, 2 times the import over export, and obvious imbalance of trade. And also note here, electrical wire, very similar, yeah? What does it mean, really? But this is interesting, builder ironmonger. Looks like we no longer produce builder ironmonger. And we actually imported a Swedish boiler, stove, and it couldn't arrive to our house for 6 months because the stove required the hinges from China. So although it's Swedish made, but component has to come from other places. Okay. Anything else that I want to say? Yeah. The recent inflation in the construction industry just after COVID and the Ukraine war has indicated how vulnerable the UK economy is. It looks like there is a sign of stagnation here. Look, that is where the COVID here dropped down here. And then when COVID finished, 2021, shot up. But there are slight supply chain problems. They continue because the supply chain problem doesn't actually make it make demand reduce demand. It actually make prices high. Yeah, so there's an inflation problem here. And now the construction industry is contracting, coming down here. So we are maybe facing a stagflation, if not recession. But why inflation matters? The cost of the imbalance of trade, let's see, that is slide 20. Let you digest this. Look at this. Yeah, real estate. The cost of imbalance of trade in the construction industry could have been affected by the overall shape of the economic structure of the UK. It shows you what the shape is. See? Anybody know what real estate here? 13.1% of your GVA is basically GDP without tax and subsidies. So you can take it as GDP. It's pretty high, isn't it? And manufacturing, on the other hand, is only 9%. I think it's around here. Manufacturing somewhere. Easy to see down here. You'll find that it's only, 9% is third here. Yeah. But when you look at built environment, as I said, how you curate the built environment, you're not just looking at buildings, you look at all the other stuff associated with buildings as well. So it's a pretty big chunk of our GDP or GVA. Okay. So UK, if you look at that, we don't even mine anything. Agriculture is so little, where our food rely a lot on import. And, I would say something like the UK doesn't make much of anything, really. So this is what the Bank of England summary about the business condition of the construction industry. It's I'm not reading all of it, I'll summarize it for you. It basically says construction output volume is falling. Orders continue to decrease a slowdown of activity across both private and public sectors. The commercial building sector continued to slow and likely to contract further in 2025, while large infrastructure projects appear to be an area of strength, with energy, water, and defense contract growing. It got to be a key part. However, the constraint of this sector are utility connections. Again, I'll go back to the grid stuff. Wind farm, plugging in the wind farm or PV farm, or indeed, where to connect the source of electricity or fuel. So basically, the one sentence is the growing evidence of construction firms are failing. Yeah, not much going on. Okay, with the economic construction downturn, you might be forgiven to think that the retrofit activity could be a way to stimulate growth in the construction sector. The government would need some basis upon which certain policy decisions could be made. For example, now warm home or green deals, basically a form of government subsidies. CAR is Cambridge with architectural research was commissioned to update the cost assumption of base energy efficiency modeling, which you all use, most of you. They found that it's difficult to estimate the material of building services that are implicated in retrofit due to the topology variation. Because of the variation, also the variation specific according to each dwelling, it's difficult to put on the estimation of installation costs. And most of you, you attend our socio-technical module, you would have seen, one of the examples is about retrofit, yeah, the retrofit for future project. And you can see how individual each dwellings are. And it's very difficult to make it work sometimes. As I suggested earlier in this presentation, I will not be able to give a detailed account of the financial sectors, how they influence in the built environment today. But this sector play an important role in capital investments. The growth of derivative projects, the outer layer, even more derivative project now, a major area of growth for the more services-oriented economic activity in the building industry. One of the examples is advance towards the ubiquitous green finance movement. Everybody heard of green finance? Blimey, it's going to be really important in the next decade. These two articles I dig up is opposite each other. This is actually written by RIBA Commissioner of Sociology to write that, and it's quite critical. But this one is by, I think, World Business Council. Built environment. So this is all very positive. So we got to read both sides, I think. Yeah. So I can't go on to it, but finance is very important, please. Please pay attention to it. So you can see, I think, with this brief talk, there's a dynamic here, and the system is multi-layer and complex. And it's related. I mean, if you can't actually invest in mining, you can't actually get things out. Yeah, you can't have whatever stuff that you want to make. Well, you have to import, obviously, somewhere else, or go somewhere to find them, in Africa or Russia or Ukraine or whatever. Let's move on. Everybody familiar with this graph? If you're not, you ought to be. If you're interested in your country, this country, and any country, it's from our World data. I checked, it haven't changed very much. Although UK is very proud of its progress in green energy, that we have nearly 45% electricity supplied by renewable. BASE always said that, but they measure what? They measure the best day in April. Yeah, some days are not that wonderful. And you can see here, the whole world is only about 14%. This slide tells us we have a long way to go. So sorry, Bob, your little stick of blue, maybe a little bit shorter. This slide, and then far from replacing fossil have been increased all the time as population increase and people, different countries started to develop. They need these things to build the infrastructure, yeah, all over the world, particularly developing countries. They obviously, these things, play a large part of our life still. So, does the stage theory of energy transition hold water? Yeah? Does it go one replacing the other? I'll let you to think about it. I'm not giving you an answer. I'm just saying, laying out some pointers for you to consider. But as research student, research is about questioning. If we accept built environment is deeply entangled with both material and non-material reality, what option does the UK have, given that it is not self-sufficient in material and mineral for a transition? We said, well, we've got to build more battery. Well, where the battery going to come from? If we accept a healthy economy is an economy with balanced trade, how can a nation with national debt to GDP ratio of 98%? In fact, they just massaged the figure. It was about 100%. But hopefully they want to make it lower down and increasing taxes so it balance the sheets, you know. Is the stage model of energy transition helpful, given that we still need fossil fuels and mineral to make stuff for transition? We're focusing solely on carbon and carbon emission to contribute for tackling the complex predicament that we face. I'm not saying that climate change is not happening, not saying whatever, but as according to some theory, peak oil theory or peak cheap oil theory, that we are in a decline of fossil fuel. We might run out of it before we build our own raft to crossing that river. I always lecture, always talk with a fun slide. This is our mystery slide for you today. Can you see that? British economy is highly London-centric. What does it mean? Finance, like Wall Street. The city of London, that square mile, is very rich. In fact, one of the Daily Express newspaper, I look on the train, pleaded the City of London do more for these little places down here. So if our economy take away City of London, GDP, we are, these places, just as poor as Mississippi. All right? So I leave you to think about this and to see why we get to where we are and how our research agenda could be expanded to include some of these interesting questions, yeah, or I call socio-technical questions. And it's not easy, but it's very rich. And you have 25, 30 years of research agenda here. So I finished. Thank you. So we can do our Q&A. You want?
Okay, we can begin the Q&A now.
Yeah.
I can come to the front and pick people if you want. And then Neely will tell us if there's any questions online.
This is, by the way, is Financial Times. You can actually download this. Okay, there's an article on it. Most of these stuff are widely available. You just need to go and find them.
I'd also like to add that we have a QR code which you can scan when you find the time to possibly put in anything you would like to get from future seminar events or similar questions like that, if you could please. So any questions?
Okay.
Yeah, thank you very much. Both very interesting. I've got a question for Bob. I hope you didn't answer this in the first half hour because I couldn't be here. But there's the sort of mantra, isn't there, like having a good balanced mix of energy sources. We need a good mixture, not putting our eggs in one basket. But I think you're imagining a future where we do just have solar and wind. And it seems like we have had a mixture in the past, maybe not deliberately, but because as one thing is going up, another thing is appearing and starting to increase. I mean, if we're assuming that the future is like the past, does that mean that in 40 years' time this mystery new thing is going to appear and it'll start going up?
I think there are three questions there, an observation and perhaps two or three questions. So first of all, the observation is that we don't only use one form of energy. For our present energy system, we use a mix of forms of energy, and they are directed to end uses that they are particularly suited to chemically, physically, economically, in terms of cost. So, for example, there's still, I seem to remember a significant amount of coal which is used in the manufacture of cement. I'm sure that's related to the way cement is made by grinding and heating and so on. There are things that will always be quite difficult to do with electricity. Air travel is the obvious example, but there are other end uses which may be, which are likely to be difficult to electrify. One of the ways around that problem is to make synthetic fuels using electricity. Now, in principle, if you have enough electricity, you can make almost anything. In practice, knitting together the supply chains that you would need to make all the different products for a modern, complex economy will take time. I think one of the constraints on the enthusiastically upward graphs that I showed you earlier is that it understates, underemphasizes, underestimates the amount of time it will probably take us as a civilization to put together clusters and bundles of technology to do the really complex tasks that you see present in real economies. Did that sound like an answer to your question?
Yes, yeah, very interesting, yeah.
I mean, part of what's going on there is an evolutionary process. So many minds focusing independently and together on complex problems produce complex technological solutions, which are obvious once you have them, but which take time to piece together. Again, you can see this happening in the Industrial Revolution. It took some time for people to work out how to use coke from coal to make iron and steel. It wasn't obvious that that was going to be possible. The problem was solved, and that detached iron and steel production from the constraints of forestry. That was a really important step forward. And it took a lot of experimentation, it took a lot of courage and a lot of risk-taking on the part of people like Abraham Varden to put together that particular bundle of technologies so that we could then displace forest products from iron and steel production. Similarly, it wasn't obvious at the beginning of the Industrial Revolution that it would be possible to make nitrogen, to fix nitrogen, using fossil fuels. It turned out to be possible, but it wasn't until the early 1900s that that particular process was cracked, and so on and so on. So these bundles of technology are absolutely crucial, and putting them together takes, crafting a new economy is more than just finding one-for-one replacements of something for coal and something else for oil and something else for gas.
I would add here, Bob, even you get to, say, 100% electrification, the world that you see at that time will not be the world like this.
Yes, yes.
Right? You have to think about that, how it affects life, society in this planet. So it's quite serious stuff, really. Either you believe that we will be running out of oil or fossil before we can actually build up the renewable to let us go to, you know, decarbonize, if you like. But how to substitute those stuff, particularly like plastic? Yeah, we're so reliant on plastic to the point that when I go and then we try to eliminate it overnight. And when I went to John Lewis's and tried to buy something, and they took away the plastic bag outside the duvet cover, and I said, "Can I have that? Because I needed to go outside because it's raining." Oh, no, you can't take plastic outside. I thought, heck, you see, this is the kind of obsession that we have now, completely devoid of reality. Plastic has a use, yeah? Without plastic, we can't really do any of these things, yeah? What are we doing? Yeah, plastic, yeah? Everything, go home and look at around you. Loads of plastic and glass.
It's very hard now to find clothing which doesn't contain elastomers, for example. Very hard to find cotton jeans.
Yes,
you can have cotton jeans, but they contain other stuff.
Yeah.
So plastic gets everywhere.
Yeah, try to live a pure life. It's very difficult. Yeah, but we tried, didn't we, in our young days?
we flirted with the group.
Yeah. Well, anyway, but I'm saying that pay attention to the material and mineral that you require to take us there. And we might not have them. And, you know, you might, I mean, particularly UK, we don't have them. Yeah, 1% mining GDP. Oh, sorry. Sorry. Hi, Herman.
Hi, yeah, hi. First of all, thank you very much for coming all the way to Loughborough to...
Not that far. I mean, it would have been more difficult 150 years ago.
2 hours.
Coaching horses, but today we came by train instead.
But still, we appreciate your time. And by the way, my question maybe is related to both, so please feel free to answer. You know, Bob, your talk about, you know, trying to understand and maybe predict the life cycle of, you know, new technology was very interesting. But I was thinking maybe one aspect of the game was ignored, or not, I'm not saying ignored, but because personally I'm a little bit, you know, pessimist about future in the sense that, you know, if you want to compare future with today we are living in a world that, you know, fossil fuels are mostly, not all, but mostly come from, in some sense, generated or originated in poor countries, and then they are exploited or used in rich countries.
Well said.
And in futuristic scenario, we will see that the renewable energy usually are generated in rich countries like Denmark, Germany, UK, I don't know, Australia.
I disagree.
Yeah.
I disagree with you. Carry on.
But to summarize my point of view is that I'm afraid maybe in the future we will have a, you know, community in which some country that used to survive by, you know, selling fossil fuels now striving and, you know, fighting with hunger and this.
Yes.
And
yes.
some other rich countries
yes.
not only do not need to purchase any more fossil fuel, also they can sell energy, sell electricity, you know. And these economical and political challenges can affect the, you know, formation of your S-shaped, you know,
yes.
life cycle.
But this is the reason why I showed one of my last slides, showed the Artetian-Nakachevich graph with a series of wars across the top, punctuating the transitions. And what we saw there was the opium wars, for example. One of the slides I didn't show was the painting of HMS Nemesis in the Pearl River, one of the first steam-powered warships, really successful steam-powered warships, which destroyed the navy of the Qing Empire in an afternoon. Yeah, and it was able to do that because it could maneuver, because it was very fast, because it had the latest, most powerful artillery on board, and so on and so on. So you're absolutely right. The reason I hesitate when you said that the countries of the future might be places like Denmark, possible. Denmark is in a particularly windy location, but I think the places that will really benefit from large-scale renewables are likely to be places like Saudi Arabia, for a number of reasons. Mainly because it's sunny in Saudi Arabia, and solar arrays would not be in competition with things like food production in much of that country, and in other parts of North Africa, because we're looking at desert for the moment. There is much more solar radiation available to the planet than there is wind energy available for obvious reasons. Okay. Think about the efficiency of the global cargo engine, which is turning solar radiation into wind. Think about the temperature difference that that cargo engine is operating across. Do the sums and estimate the efficiency of conversion. It's not very high. And in fact, it's much less than common.
But you're also thinking, in a way, is very technological deterministic.
Yeah.
You need to have human capital.
Yeah.
How do you think Saudi Arabia now being built? By what? China's PV and Philippine and Indonesian labor, right? They don't have enough people. Yeah, you understand that then. When you start looking in this kind of context, you need to look at some of the human capital that actually make economy work. Yeah, and there are crises in Europe. The people are leaving Europe for other pasture. Germany is in economic crisis. Yeah, Volkswagen and Mercedes-Benz moved to both. BASF move out of Germany. Where, I mean, the next generation of engineer, next generation of skilled people will be destroyed.
If I can come back to your comment about populations, where the density of population now is in industrialized countries. Where was I going with this? Yes, the reason Britain has such a high population density is precisely because it was able to use its industrial strength based on fossil fuels and coal to build the world's biggest navy and one of the most successful armies in the world, and it was able to colonize other places. It is not obvious that Britain will be as successful in the rest of the 21st century as it was in the 19th century. Conversely, places like Saudi Arabia have seen their population grow from something like 6 million in the middle of the 20th century to something like 35, I think, million now, and will probably continue to grow. Because if you have lots of sunlight, you can make electricity. You have oil remaining to fund your transition, and in principle, you can grow crops. Water might be a problem, but if you are able to make use of high-tech agriculture, maybe you can do it. So I suspect we will see a different population distribution at the end of the 21st century than we had at the beginning of the 21st century. And we'll see where it goes.
That's right, that's right.
Honestly, you're so lucky to be alive and young now, because the next few decades are going to be an absolute blast. You might have thought that the 19th century was exciting, but the 21st century may well be even more exciting than the 19th century was. The 20th century, in many ways, was a period of relative calm. He said, what an outrageous statement. Because the locations of the industrialized countries stay much the same, well, much the same at the end of the 20th century as they were at the beginning of the 20th century. Things didn't shift around that much. Africa remained poor in the main. India was still relatively poor at the end of the 20th century. China was poor at the end of the 20th century. Now everything is changing and in flux. The 21st century is going through, and it could be at last, in non-metaphorical terms, if we're not very careful about how we manage geopolitics over the next few months. But it will be a blast experientially for you if we get past the present bottleneck and the present risk.
Sorry, I cannot resist to ask you. In your opinion, in the way you see the future work, do you think that in the world that most or all of the energy comes from renewables, do you think the gap between?
No. It's a maybe. I don't see it as will. I see it as maybe.
Yes,
yes.
Okay, that's a better way. If or most of the energy comes from renewables, do you think the gap between poor and rich countries will increase or decrease?
Yes and no. I think some places will become poorer. I can't see at the moment an overwhelming reason why Britain would expect to be the third or fourth richest country in the world by the end of the 21st century. At the moment, I can't see that. I can't see an explanation for that. Maybe there will be one. Maybe we will find one. Maybe we will continue to make bad comedy shows or television, for example. Perhaps a resurgence of faulty towers or something. There does seem to be something particularly pathological about British humour, which may result in a market. But we don't seem to make very much. So I'm going to say the obvious. I suspect that China will probably be the dominant power worldwide, economically, industrially, and possibly culturally, although we will have to do something about teaching the rest of the world to read Chinese characters.
Yeah, that's what they worry about, is they have to learn Chinese, I'm afraid. No. Seriously, I mean, if you want to actually look at which country can surviving, I mean, with the oil is diminishing, gas diminishing, material diminishing. And one thing to bear in mind, the lower layer of the material and resources, they are not equally distributed. They're lodged everywhere, different parts of the world. So look at those maps, look at them, and why are we having a war like this at the moment? Still no resolution, yeah. And what happened to Europe? Yeah, it's hard. It's hard to actually facing this. Yes, it doesn't bring me any pleasure. You're seeing this when people are getting killed all the time, and what we're doing there. Yeah, and look at where the oils are. Yeah, oil fields are. Look at where the gas fields are. We need them. We're not getting anywhere near renewable. We need those to make PV and heat pump. Do you know, I mean, you've seen the heat pump gubbins. They're huge. You know, one house is full of the steels and tubes and everything. And you know the PV market share? China has most of the market share. They have their internal market. Heat pump, they also have. They got 1.4 to 5 billion. So that is important with population. If you
just to go back to China, one of the advantages that China has is that a large part of China is at fairly low latitudes, and so is well placed for tech. Obviously, China is also working on things like nuclear, and the moment has to import most of its fossil fuels, so it has a strong incentive to move in the direction of nuclear and renewables.
Yeah.
And it has the potential to do so, because it's, as I say, it has parts of the country are below the tropic, the northern tropic, whatever that's called, the cancer capital.
And I don't know whether you know it or not, the last 10 years, 10 years, United States is actually saved by the shale oil. Yeah? And I mean, you got to find out that because the oil, the proper crude oil is actually not producing very much.
One of the things that we started to talk about in the last few years is not the idea of peak oil, but peak cheap oil, which I think is it's quite an interesting distinction. So traditionally fossil fuel has been relatively cheap, and that's has been reflected in the historical crude oil price, and the fact that crude oil producing countries could become fabulously wealthy because there's lots of rent available in the oil market if you could extract it. But I think things like shale oil are much more expensive to get out, reflected in the lower energy return on energy invested.
Yes.
I'm often might have a different perspective. Doesn't it seem maybe a lot of the conversations, humorous question about transition to renewables are going to benefit countries? We keep boxing up the map into countries. Is it not wiser now? Is that not old-fashioned? Now we should be thinking about the actual investment firms that own and operate all of the energy supply chains and infrastructure around the world. Because iPhone had a great slide on the economic disparity in the UK, and that just shows, well, why are we boxing people to being in the UK? Why not letting China, India, the UK, all these different countries, the oil fields or the resources that are available in these countries are owned and operated by the same companies, by the same huge globalized companies. So they're the people that we should be more concerned about, not which countries are going to benefit, but inherently these companies benefit. And these companies own the resources from all over the world. So.
Well, you know that most of the BP is not really British. Yeah, you know that already probably. Most corporation, I think there is a kind of illusion that when we say Britain, that is Britain. In fact, the North Sea oil, right from the beginning, is not British. It's Hamilton who bought the field already. We only ever earn the money on licensing. Yeah, the UK earn that in licensing. So quite a lot of things is not ours. I mean UK, yeah? And again, you have to look at the layer, as I said, the layer of economic activity and finance, the capital, the liquidity, the M1, where is money flowing from where? And why is this lower interest rate is important, or high interest rate is important? Why is inflation is important? Why we have to bring down inflation? All this question is very, very important for the transition. It's about capital and investment flow. If you don't have that, your dreams won't come true. Because basically now, Britain have high tax environment, and the Labour government actually lower our interest rate. And we also very belligerent in our dealing with foreign policy. Investor wouldn't want to actually invest in UK. The capital, the investment will flow away. A lot of people, have you heard today, Luton factory is going to lay off thousands of people. Is it because they will go, yeah? Yeah, car factory. And also car and like pharmaceutical industry. You cannot operate in now the electricity. It's not energy intense enough. I mean, you look at oil refinery. Yeah, it's so many things that we do.
I mean, you can operate with electricity, but the raw materials, at the moment, the supply chains are very complex and typically involve other. Yeah.
I show you those 3 slides about timber, glass. It means hundreds of partners with some big partners. Everything is actually interwoven everywhere. Little component here, little component there. Your phones are made up with 156 components, more than that one maybe. That is impossible to separate them. And that's what I'm saying. It's impossible. Some of you want to do life cycle analysis, it's really hard. And master thesis. They try to do a psychoanalysis of a scooter, and ostensibly from Germany. But there are lots of things that they cannot find out where the component came from. So it's very difficult for carbon footprint, you know, to put carbon footprint in those components. It's impossible. The globalization process will go on for so many decades. And our supply chain is very, very complex. To disentangle them, it takes a heck of a lot of job, at least for the first 10 years. Yeah, you heard a lot about reshoring. It's not that easy. It's not that easy. They still do the different components, different places like Vietnam, like Thailand, well, where the labor is cheap, where there's not a lot of regulations. Okay, so I think maybe better leave now.
Okay.
So.
Well, we can now move the discussion into the atrium where we have some sandwiches and cakes, I believe.
Oh, that's nice.
If you have any further questions, you can ask them with some nice cake. And thank you all for attending. I think this has been a wonderful event, and I look forward to hosting more of these in the coming year in January, and I hope you can all attend again.
Wait a minute, Tom. I have something for you. And your fellow students. Plastic, so they won't melt. I got you, Tom. Lovely Christmas.
Thank you.
So you can share.
Thank you. We can share these
Yeah.
atrium.
Yeah. Okay. Thank you very much.
Thank you.
Thank you. Thank you for letting us, basically rent.
And I'll upload them to YouTube maybe on the weekend.
Yeah.
Thank you.
And then you can share with anybody.
Thank you.
I believe as well, we got a recording at the back of this better camera than over the corner, which should look nice.
Yeah. It's okay. Yeah, I'll give you the references in the slide tomorrow. So you can actually do it on the back.
To forward.
Yeah. So my slide hasn't got the references at the end. Mine has, but mine hasn't.
I could perhaps include a document with a YouTube description.
Yes,
For a reference.
Yeah.
That would be
I'll bring up,
good. Maybe it could just be a text document with all the references.
Yeah, that's wonderful.
Enhancing.
Oh, right. Thank you.
I've also got my fingers resistant to the tune I'm going to get, which is summer school happening in July. Giving this seminar. I don't know what you said, but maybe
Yeah, we have to share our ideas, so let's see how you take it, in the future. Because it's only something like
Okay, just for a second. Can I please take a picture with you on the online?
Yeah,
Just a second. Sorry for the
Anton. Yes.
And Raj organised the catering. He's with the cake.
Okay, so
You get the other one.
Tom wanted to take photographs.
Yes.
Very briefly, you should do it.
Yes.
Probably Raj should do it as well.
Yeah.
Don't forget Raj.
Yes, please. That'd be great.
Okay.
And Neil, do you want to have a picture?
Yeah. Thank you. So I got some picture back to you. I got the memory back, which I will give the one you know those pictures we took. And the meeting conference.
Ah, great.
This one?
Yes.
Do you remember in London? Yeah. But I had to find out.
Okay, there we go.
Have the picture of Bob and later on.
This one?
Yes.
Okay.
Look, I'm really fat there. Thank you.
Temporarily, yes, I put it here for you.
Thank you. Just leave it on the floor. Oh.
Got the picture. As an organizer. Well done.
Thank you. Thank you very much. Thank you.
Speak about this though, because you can see how much we've aged.
Thank you.
I can come back and clean up some things after. Yes.
Yeah.
This wonderful thing.
Yep. Do it.
I'll clean up the remote and the box after. That's like that.
You'll still use your sort out what training is Do you know the times of the train?
No, well, going to London there every half an hour. If you want London.
Yeah. Yes, we'll find out. We'll find out. Yeah.
I can check for you right now.
That'll be good. Yeah. Okay. Yep, I think I've got the link. Yeah. Right.
Yeah.
5:32 could be.
Thank you. What?
Hey, Matt. I'll just bring another box of cards.
Yeah.
Yeah, we can do it like a bit later.
Yeah.
Take some books.
No one's touched it.
Yeah.
cheap